Good afternoon, everybody. And this is Han from Riki in Japan, and also I'm working at FarmRight. First of all, I'm very thankful to Professor Scholz for inviting me to give a talk at ICMOVPE. So today I would like to talk about the low operating voltages as well as low efficiency drip in AlGaN UVB LEDs without using conventional electron blocking mechanism. Here is the outline of my presentation. First, I will talk about the UV LED applications, current status of UVB LEDs, and little background of AlGaN-based UVB LEDs. And then I talk about briefly the research challenges of AlGaN UVB LEDs, especially the differential resistance, high operating voltages in LEDs. And then I want to talk about the new idea of the undoped aluminum-graded EBL instead of using conventional multi-quantum bare electron blocking layer. And at the end, I will summarize my talk. UV LED has a lot of applications, and you can see for UVC and UVB and UVA. But today I will just focus on UVB. UVB can be used for immunotherapy, like atopic dermatitis, for skin disease, vulgaris, and psoriasis. We need a narrow-band UVB LED at 310 nanometer for such applications. And for the agriculture's application, I would say that pesticide or any chemical spraying can severely damage to the fauna and flora, and it may help in promoting to the new types of viruses and disease. UVB LED is a clean source of virus inactivation in agriculture crops and plants, and also we can enrich phytochemical in plants and also in some fruits and vegetables by growing under UVB light. And also we can use UVB lights for functional foods, which is very important for human health. In addition to that, we can inactivate tomato mosaic virus by using 290 nanometer UVB LED. Here is one of the research work was done by Matsura, and the work is published in Applied Microbiology. And by using 280 nanometer or 290 nanometer UVB LEDs, so they can inactivate the TOMV virus in tomato. And also the powdery mildew and mites pose significant threat to many crops, but can be substantially reduced with the use of the UV light. So UVB light has a lot of wonderful application. Also, we can use for the vitamin D3 production in human body. Here I got the cover page of the PSSA. So here is my UVB LED, which is producing 17 milliwatts. So as you know that the distribution of vitamin D3 in population living about 638 north of Europe due to less sunny days were investigated by Remarkably, and it was found that 23% of men and 17% of women had insufficient level of vitamin D3. So UVB LED with emission wavelength of 295 or 300 nanometer is quite useful for production of vitamin D3 in human body. So recently we got some feature articles in the compound semiconductors. The title is UVB LEDs refining the design. But here you can find a lot of new improvement in UVB LEDs and also the applications for medical and agriculture in this feature article. Here is the current status of our UV LEDs at Riken. So everybody knows we got the world record efficiency of 20% for LED at emission wavelength of 275 nanometer. And recently we got 9.6% efficiency for UVB LED at emission wavelength of 304 nanometer. was published in the scientific report. And also we got some impressive results for UVB LED at 310 nanometer for medical application like psoriasis or skin atopic, etc. I'll briefly talk about the real challenges of UVB LEDs. We improved some of the challenges. For example, we can make a very good aluminum nitride template with good crystal quality, and also improve the electron source layer of the for the UVB LED. And by growing quantum well on those great crystal, we can get IQE of 54%, but still is not enough. So we still have a lot of challenges like low injection efficiency of holes and low electrical efficiency and internal like the differential resistance and high operating voltages, and also by exploring new materials, possibility of the hexagonal boron nitride, or to find a new alternative for the P side of the UV LEDs. So these are a few challenges, but the most critical, I believe, is the P side. So here we try to resolve those challenges one by one. First, we grow the quantum well structure for UVB LEDs, where this is the LED structure. So the important point, we grow 3.4 micrometer thick buffer layer, which is 42% relaxed. And the electron source layer was 50% relaxed, and this was measured by reciprocal space mapping along -1, phone reflections by using XRD. So as a result, we got very good crystallinity, and the rocking curve along 002 and 102 reflection, where full width and half maximum was reduced to 311 arc second and 442 arc second. And the screw type dislocation density was reduced to 2.1 times power 8 per centimeter square, and H type of dislocation density was reduced to 1.7 times power 9 per centimeter square. So by using this new quantum well structure, we can get the IQE of 54% with the collaboration of Yamaguchi University, and by using this quantum well structure in our new LED design recently, last year we did some work by introducing the polarization doped whole source layer, where the aluminum composition as a depth is given here. And also we introduced the aluminum graded p-type multi-quantum bare electron-blocking layer, where the EBL1 were keep high aluminum contents if you compare with EBL2, and then the whole source layer. And by exploiting the polarization effect, we can get a very good electrical conductivity. And the whole density was 2.6 times power 16, and the resistivity is around 22 ohm centimeter. By using this design, we can get a high EQE of 8.2% by using medium size of the chip, and the light output power is given. But still we have high operating voltages as shown, but I will show in the next slide. And we also investigated the influence of very thin nickel part of the P electrode under the aluminum. And first we did some numerical and analytical study of the TE and T modes. Here is the reflectance as a function of the incidence angle is shown here. Especially for the TE mode and for the T mode, for 0.4 nanometer thin, we got very impressive high reflectance data. And by using in the experimental device, we use a 0.4 nanometer thin nickel in P electrode. And here is the chip of the UVB LED on bare-wafer. It's 400 by 400 micrometer square chip. As a result, we got a 7.1% EQE and the light output power of 40 milliwatt. But by using the small chip, 250 by 250 micrometer square area, with 0.4 nanometer thick nickel in P electrode, we got a world record 9.6% EQE under CW operation. But it's not the end of the story. Unfortunately, we confronted with high operating voltages in previous UV LEDs on wafer. We also realized that the MQB EBL may cause enhancement to the differential resistance. And to reduce the operating voltages, we introduced one novel design of the undoped aluminum-graded EBL in transparent UVB LEDs instead of using conventional electron blocking mechanism. Here is the new architecture and design of the UVB LED. So this is the conventional, is the new. So we just replaced this MQB, the multi-quantum bare electron blocking layer, with the new design where we introduced graded aluminum gallium nitride EBL without doping, and then magnesium doped p-AlGaN whole source layer. And with this new design, we first checked the photoluminescence spectra, and quite high spectral intensity were achieved for the new polarized EBL layer, which is one of the indirect indication of better radiatory combination in the quantum well. Next, we fabricated the LED device on bare-wafer, where we introduced the indium dot as an electrode, and nickel gold as a P electrode with size of 400 by 400 micrometer square, and the real device shown here. So the electroluminescence spectral intensity was enhanced again in the new polarized EBL case, and also the operating voltages were reduced from 80 volt to 30 volt in this case. And furthermore, the output power was linearly increased, as shown here, if you compare with the conventional electron blocking. And very interestingly, the EQE was, there was no efficiency droop, you can see here. And of course, here it was a little higher, but this could be the low energy electron in the quantum well could be the possibility. And a very low efficiency droop was happen here. So with this, I will summarize my talk. The operating voltages under 260 milliampere drive were greatly reduced from 80 volt to 30 volt by using a new polarized undoped aluminum graded ABL. The efficiency droop was greatly suppressed in the new polarized EBL LED too. The emitted light power of LED was varied linearly, even under high current drive of 500 milliamps on bare-wafer. This was for the first time for us. And the next target is to introduce the same strategy to the 227 nanometer far UVC LED, and also some others LED at different emission wavelength. This is our future plan. So we would like to, thanks to the NATO Japan, which NATO stands for the New Energy and Industrial Technology Development Organization, and we also thankful to Nippon Tungsten for their partial support. And thank you for your kind attention.